Let's apply the system concept that we discussed earlier to the topic of understanding and predicting motion. To this point, we've focused on a single moving object. Let's choose that object as our system. We've learned to describe this motion of the system's average location, but we need to know more to predict motion. For example, there may be some other qualities or properties of our system that may be important. Additionally, there may be something else outside of the system that can interact with the system and affect the system's motion, so we may need to know about that too. Let's handle these issues in turn. First, let's discuss the system itself. When we're trying to predict the translational motion of our system, there's only a single property that we're guaranteed will come into play in most every case. That property is the system's mass, which, for our purposes, we can think of as a measure of how much matter is contained within our object. Mass has the dimensions of mass with corresponding units of kilograms. Mass is a scalar quantity that is always positive. Next, let's discuss the interactions between our system and its surroundings. Again, we can likely imagine a gazillion possible ways that can happen too. It turns out that the relevant interactions for understanding and predicting motion are captured by only a few major concepts, and we'll start with one: the concept of forces. A force is a push or a pull, which we know intuitively requires two pieces of information to specify: the magnitude and the direction. So, no surprise, a force is a vector, and we can use an arrow to represent a force. Note that the arrow's length does not represent the dimensions of length, but tells us how big or how small a force is. We'll discuss the dimensions and units of a force in a moment, but for now, remember that we have to make an extra decision about how long to draw the arrow to represent a particular magnitude of force. And after that, we can draw a longer arrow for a bigger push or pull, and a shorter arrow for a smaller push or pull. Now, there may be lots of forces acting on our system. What's crucially important for understanding and predicting translational motion is the total push or pull acting on our system. The net force is the sum of all the pushes and pulls from the surroundings acting on our system. If we have arrows drawn to represent each push or pull, then we know that we can place the arrows head to tail in any order that we like to find the net force on our system. Here are a few tips to keep in mind. Depending on the situation, there can be items in the surroundings that exert no force, other items that exert only one force, and still others that exert more than one force at the same time on our system. If we're adding individual forces to get the net force on our system, we have to make sure we include all important forces from the surroundings acting on our system. While the system itself can exert forces on the surroundings, we never add these forces to find the net force on the system. We only include forces from the surroundings acting on the system. The system cannot exert a force on itself, so let's make sure we don't mistakenly include something like this when we're discussing the net force on the system. Now we're all set to introduce the fundamental principle which will allow us to understand and predict translational motion in a wide variety of cases. That principle is Newton's second law, which says that if we watch our object and measure the change in the velocity during some change in time, then the ratio of the change in velocity to the change in time is equal to the total pushes and pulls on our object divided by the mass of the object. Right away, we can apply dimensional analysis to Newton's second law to determine the dimensions of force, which we see are the product of mass times length divided by time squared. The corresponding units that we'll typically use are kilogram meter per second squared, which together have been given the name of the Newton. Now, when we draw an arrow to represent a force, we'll know what the arrow's length means. Newton's second law is an amazing statement which relates something we can obtain just by directly watching our object move during some time interval to very different quantities that we cannot generally get at just by looking at our object. Let's emphasize here that there may be lots of items in the surroundings exerting lots of pushes and pulls, but at the end of the day, all we care about here is the total push or pull, the total force. This will be very powerful for us when we face important situations where we really only have to deal with one force, the total force, without even knowing or caring about the specific pushes or pulls, which often we can't see, that add up to the total push or pull, which we also typically can't see. We'll come to examples like this very soon. Let's end here by saying a bit about what makes Newton's second law a law. First, Newton's second law is a law because it tells us a secret of the universe. It's not obvious that quantities that describe motion should be related to object properties or the influence of the surroundings in this particular way. Second, Newton's second law is a law rather than somebody's opinion or a wild guess, because it is a statement about nature that has withstood the test of countless experiments with moving objects over a wide variety of conditions. This means you don't have to believe it just because I told you so. You'll have plenty of opportunities to check this for yourself, beginning with seeing whether Newton's second law can be used to predict the future for moving objects. We'll get started with that in our next segment.